Good morning, students. Today we are here to conclude our syllabus of soft computing by covering some very important topics of artificial neural network, which we have left in the previous class, and that needs to be discussed very much. On this note, I will start today's class with multiple adaptive linear neurons. As you can see that this neural network is often termed as Madaline network. As its name suggests, basically it consists of many Adelines neural networks, and those Adelines neural networks are incorporated in parallel. And here also this Madaline neural network is having a single output unit. In this very case, these Adeline neural networks act as hidden units. That means hidden layers, you can say. And those hidden layers are incorporated between the input layer and the Madaline layers. Now, weights between these Adeline and Madaline layers are usually fixed. That is positive. And it poses usually equal values, and a bias of 1. So what happens that we have, 3 layers now. One is input layer, another is hidden layer, which is Adeline layers, and the third one is output layer, which is Madaline layers. So what happens, usually, the weights between this input and Adeline layers, those weights are adjusted during training. And this training, you can see that this training can be done by using delta rule, which we already covered in the previous class. Now, if you closely observe this particular network, this is the Madaline network, you can see that these are the, input neurons, you can say. That means the input layer. These are the Adeline networks or the hidden layers, where you can see that there is a connecting link between the input layer and the Adeline layers. And also there is a bias neuron as well. And you will obtain a single output neuron, which is the Madaline neuron, and it is also having a bias neuron or bias unit input, you can say. Now, how does this Madaline network work? As we have already studied, that all the weights, all the connecting weights, that is V1, V2 up to Vm, all those connecting weights, and the bias, V0, that enters into the output neuron, then means the Madaline neuron. Y are determined, that means the output neuron is determined so that the response of Y, that means the output neuron, is 1. And all the weights entering into the, the output unit, that is the V1 equal to V2 and up to Vm, that is to be treated as half. And also bias B0, which is coming as another input to the Madaline neuron, that is also taken as half, so that the summation of these two, all the weights and the bias, will be 1, so that the response of Madaline neuron will be 1. So the condition is satisfied, and to satisfy this particular condition, the activation for Adeline or hidden unit and the Madaline unit, which is the output unit, the activation function is given as fx equal to 1 if x is greater than equal to 0, and it is equal to minus 1 if x is less than 0. So in that very case, the training process of this Madaline system is very much similar to that of an Adeline, which we have covered in the previous class. Now coming to the next network, which is a very popular network. You can hear about this particular network in many places. if you are working with artificial neural network. This popular, very popular network is called Hopfield network. This is a kind of network, where there are every, networks are fully interconnected. Those networks are auto-associative, and those networks are fully interconnected single layer feedback network. So we can say also it is as single layer, recurrent network. So this particular network, has been utilized as first analog VLSI neural chip. So this is a very, important, uh, thing, or, discovery in the research of artificial neural network, so that we can, utilize any kind of artificial neural network as a chip or as a neural chip. So basically, whenever it is used as a chip, it is also applicable as associative memory, because it has a memory, obviously. So it is applicable for this kind of memory storage, and it is useful in different optimization problems, like traveling salesman problem. So this is, a different context where artificial intelligence are being discussed. So I'm not going very deep into it. So coming back to what Hopfield network is all about, this particular network, is of two types. One is discrete and another is continuous. If you look at this particular, slides, which gives you a sense of, discrete Hopfield neural network, then you can see that there is some, neurons, and you can see that all the inputs like x1, x2, xi, and in that particular, fashion up to xn, that is coming, and from all those neurons, all the outputs are coming out as, y1, y2, yi, yn, like this. Now, what is very, unique in this particular network? If you closely observe, then you can see that there is a kind of, feedback condition or recurrent, loop. So what does this mean? This means that this particular network, takes two valued inputs. That means either it takes binary at some particular time. Sometimes it takes bipolar as well. That means either zeros or ones, or sometimes, plus one and minus one. In this particular network, you can see that it has symmetric weight with no self connections. That means it has no self loop. But obviously, it will have a kind of, recurrent connection or feedback path. So how does this particular path, form? Coming to that particular, point, what we can see here is all those weights, are symmetric. So we can write that Wij equal to Wgi. And obviously Wii equal to 0. That means there is no self connection or self loop. So automatically there is no such, weights associated with the self association or self connections. In this particular network, you can see that only one unit updates its activation one at a time. There is no simultaneous process can be happened. So each unit continuously receives an external signal. Along with the signal, it receives from the other unit. That is the main thing which we can see here, that this particular, for this particular neuron, it is accepting a particular, signal from the external as an external input, and also, it is having, all the inputs from all other neurons as well. all other universe as well, right? Now what happens that the outputs from each processing element are fed back to the input of the other processing element. So that is why each unit continuously receives the signals from the other units as well. But in this very feedback process where the outputs from a particular processing elements are getting fed back to the input of the other processing elements, we can see that there is no feedback path to itself. That is why it is called that there is no self connections. And here you can see that the connections are either excitatory or inhibitory. And we have this kind of, concept of excitatory or inhibitory in the previous class. Here, what does this two term mean? Excitatory means that the output is similar to the input, and inhibitory means the output differs from input. Now, whenever we are talking about continuous Hopfield network, how does it differ from the discrete one? That is, here the time is assumed to be a continuous variable because this is a continuous Hopfield network. So automatically the time is a very important variable, and this is obviously a continuous variable. Now the network has nodes obviously, and those nodes have a continuous output, which is a graded one, rather than the two-state binary output what we had in the discrete Hopfield network. So in that particular network, what you can see is the energy of that particular network decreases continuously with time. And this, since this is a continuous Hopfield network, so this particular network, can be realized as an electronic circuit where you can see nonlinear amplifiers are there, resistors are there, and all, if I say that we have n number of amplifiers, we have some input voltage like Ui, we have some output voltage Yi for this particular electronic circuit. And obviously, since this is a neural network, so obviously we cannot forget about activation function. And if that particular activation function is the function of the input voltage Ui, then this activation function can be a sigmoid function where this G of Ui can be represented as G of sigma Ui. And whenever this particular thing, this sigmoid function can be represented as this. Whereas you can see that this particular, whenever we are talking about the sigmoid function, we can have this gain parameters. And all these gain parameters, are needed to utilize this particular continuous Hopfield network as an electronic circuit where we have all these electronic parameters. Now, whenever this Hopfield network, that means a sense of, feedback network or a sense of, you can say, recurrent neural network has already come into our mind. So now we are quite ready to deal with backpropagation neural network. Whenever we are talking about this particular neural network, that is the backpropagation neural network, then we can expect a particular, this kind of signal flow through the network. If you can see here, this is the backpropagation training algorithm. So here you can see that we have a feed forward path. So obviously network activation forward step. And we have also one, recurrent path or, feedback path as well. So in that particular backward step, what happens that error is being propagated. So that is why backpropagation algorithm, adjusts the weights of the neural network so that it can minimize total mean squared error. Now, before going to the backpropagation neural network, so okay, fine. So we can at least, you know, discuss about the basic construction of the BPNN, that is backpropagation neural network. But going deep into that, we will first discuss about some few more important terms so that we can understand this backpropagation neural network training algorithm in a better way. So coming to the basic structure of this backpropagation neural network, you can see that this particular network has three layers, as we had in Hopfield network as well. That means obviously the three layers we know now, that those layers are obviously input layers, hidden layer, and output layer, right? So if I say that the nodes of the input layer is, let's say, represented by I, and the nodes of the hidden layers are represented by J, and obviously the nodes of the output layer is represented by K. Then what happens? We have automatically some connections between the input layers and hidden layer, and similarly some connections between the hidden layer and the output layer as well. So if I and j represents the nodes of the input layer and the hidden layer, so wij refers to the weight of connection between a node in the input layer and the node in the hidden layer. So why we are so concerned about it? Because, by dealing with this particular, weights, we can, derive the output value yj of the node G. And you can see where again we are going to take the sigmoid like function. Now, what is xj? Xj can be computed as the, each and every, input for node I, that means for the input layer, multiplied by the weight vector between the input layer and the hidden layer, minus theta g. Now this theta j is the threshold for node G. And obviously this particular, process is being repeated for I equal to 1 to n. That means we know that I is basically the nodes in the input layer, and n is the number of inputs to node G. So automatically for all the inputs which are going to node J, for all inputs, we will follow this particular process. Now, in case of backpropagation neural network, you can see this gradient descent learning. And we have, as you can remember, that we have also, introduced this particular learning. We have mentioned this particular learning in the previous class, where we have told you that in this particular, time frame, what happens that we have an initial, position. After a certain time, we have a final position as well. So we can, predict, or we can, evaluate what is the weight at this particular final position. And we can, evaluate this Wn as W0 minus eta into daily by del W. So we know here that this gradient descent learning, works on some differential manner. And here, a very important, parameter, which is eta, that lies in, 0 and 1. So what happens when this gradient descent learning comes into the picture? This particular, learning is usually a first order iterative optimization algorithm which can find a local minimum of a differentiable function. As we can see that this daily by del W function, this is a differentiable function, right? Now what happens that if I want to find out a local minimum of a particular function by using this gradient descent formula or gradient descent learning process, then what we need to do is we need to take steps which is proportional to the negative of the gradient, or we can say this is the approximate gradient, of the function at one specific point or at the current point. So if this is going to be happened, then you can see here that we are going to, using the negative of this particular differential term. That is what, this particular paragraph is saying. Now, what happens when we are going to measure total mean squared error? Now, first question may come in your mind that why do we need to measure such error? And where does this error come from? So now what happens that whenever we are going to use this gradient descent learning into an artificial neural network, that means very precisely in a backpropagation neural network, then what happens that we have here a certain kind of, inputs like from x1 to xn. We have also some associated weights, that means w1 to wn, which we know that we are going to sum all these, inputs and obviously multiplied by the, weight vectors. And this is something, the net input which is coming to the neural net. Whatever be the output of the neural net, now we know that whenever there is a feedback process, that means automatically there must be a target or a desired output, and obviously we have some output which is obtained from the neural network, and constantly or continuously we need to, find whether there is any difference between these desired or target and the obtained outputs. If we find any kind of difference, that difference is termed as error. That is why here it is mentioned that this error is nothing but this desired minus this net. And here, this E, that is the energy, which is, basically is going to be differentiable. That is half of this error square. And this particular error, is going to feed back to the input side so that the weights can be adjusted in order to minimize this error. So this process of updation of weights is just, expressed a few times before. And now this is the error which we want to minimize in this process. This error is called total mean squared error. Now, here, what I have just told, if you can map that learning with this particular slide, then you can find that I have just mentioned that this is the error, of output neuron K after the activation of the network on the nth training example. That means obviously if that is the current training example, that means if that is the order of the current training example, that is the n. So obviously the input may be defined as xn, the desired output may be defined as dn. So automatically the error for this neuron K at nth training example is obviously described as dkn, that is the desired one, minus the opt-in output one. And as we can see from the previous slide, the network error is nothing but the sum of the squared errors of the output neurons, where this En equal to summation of ek square n, and total mean square error, which is the the fundamental one which we are looking for here. So that total mean square error is nothing but the average of the network errors of the training examples. So if we have capital N number of training examples, so obviously this small n, which is the nth training example, so this n must be run from or repeated from 1 to capital N, and we are going to take the average, that is by 1 by n, and this is the En, that is the network error. So this is what the total mean squared error all about. Now, if that error is already calculated, now the process of weight updation is going to be started. Now the backpropagation weight update rule is usually based on gradient descent method that we have already known. So now we can understand that this particular method takes a step in the direction yielding the maximum decrease of the network error E, and this direction is the opposite of the gradient of E. That is why we can write this minus eta del E by del W. And the iteration of the backpropagation algorithm is terminated when the sum of squared errors of the output values for all training data in an epoch, or you can say in a training session, is less than some threshold value, and threshold value is like 0.01, you can say. So here what we can have is, we can update our weight, which is the symmetric one, that is Wij, that is equal to Wij plus del Wij. So this is something which you can you can find a kind of variation in weight, and when you add this variation in weight with the current weight, you are getting the updated weight. And this del Wij is nothing but that what I can say, that that opposite of the gradient of E. I mean this particular gradient descent rule evaluation, that is minus eta into del E by del Wij. So in this manner, weights are updated in backpropagation learning algorithm. Now, how long it will run? So automatically there must be some stopping criteria. So stopping criteria are usually based on these two criteria, like there must be a particular time where total mean squared error change. That means obviously that backpropagation algorithm is considered to have converged when the absolute rate of change in the average squared error per epoch is very, very, very small. That means it is like negligibly small. That means in the range of 0.1 or 0.01, like that. Then we can stop this particular learning process or training process. In another approach, what we can do is, after each training session, after each epoch, the neural network is let for testing for generalization. If you can see that the performance of this particular neural network is adequate, then you can stop the training session. If this stopping criteria is used, then the part of the training set used for testing the network generalization will not used for updating the weights. That means if you can apply this particular topping criteria, that means after each training session you are going to test the artificial neural network, so automatically you must need some data set for testing as well. So in that particular case, beforehand you have to segregate the whole training set into two parts, where a small part is required or is reserved for testing purpose, so that the weights for those training sets won't participate in the process where you are going to update the weights of the training set. So that means all those particular testing set must be different from what you are accomplished as training set to train the neural network, and also to test the neural network, to judge the performance of this particular neural network with the result testing set. So whatever we are learned so far, we can utilize this particular learning with an example. How? You can see a picture below. As you can see this particular picture, you can see that these are the inputs. This is first layer, you can see, and you can see that all those symbols like WXMN, this is a generalized one, which is written here as WX11, or you can write as WX21 in this fashion. So what happens that here, as you can see, that all these weights represents the weights of connections between network input XM, that means X1, and the neuron in the input layer. So that is why what happens, that whenever you are going to indicate this particular connecting links or connections, then this WX1, X1 means the input from where this particular connection has been drawn, and 1 means the target neuron in the input layer. So this is F1 neuron, that is why it is written here as 1. Similarly, whenever you will go with this particular connecting links, you can see this is X2, this is the initiating neuron, you can say inputs, this is the inputs, and obviously the targeting neuron in the input layer, that is 1, that is why it is WX1. So in this fashion, what do you expect here? You can expect a particular output from this particular neuron as Y1 equal to function of F1 as WX11 into X1 and WX21 into X2. So this is what you can expect as an output from this particular neuron. Coming to the second one, when this particular neuron is in the picture, then similarly, this is what your connection is. So basically this is WX1, 2, this is WX2, 2, and this is the target neuron as F2. So what happens that we can expect an output y2 is equal to f2, that is wx12 multiplied by x1, and wx2 2, obviously, that means the targeting neuron is 2, multiplied by x2. So in this fashion, we can compute what can be the output from each and every neurons. So moving forward with this particular idea, we can have y3 as well. We can have y4 as well, because here three connections are basically coming. So this is propagation of signals through the hidden layer now. So obviously the rule is same here also. So we can have y4 as well. We can have y5. We can also have y6. So now in this fashion, propagation of signals through the output layer is also completed, starting from the input layer. So now what happens whenever this computation is complete? Then in the next algorithm step, we have to, calculate whether there is any error. That means whether there is any difference between the desired and the obtained or this computed output. So whenever these two output values are compared, then we can find that there is a difference, which is called the error signal, which is the, particular this del error signal of this output layer neuron. Now what happens? Since this is a backpropagation neural network, so this error must be propagated from the output neuron to the input neuron, following the same path but in the opposite direction. In this way, then this del is started to move backward. And we can see that now this del 4 is what? This del 4 is, if this is the weights associated with the connections, then this weight must be multiplied by the del. So this will be the del 4. So if this is the process, then we can also compute this del 5. Let's say W56 is the weight associated with the connections here. So automatically this del 5 is nothing but this weight W56 multiplied by del. Similar fashion, del 1 is also computed. Del 2 can be also computed. Del 3 can also be computed. Now, in this particular phase, you can see that whenever we are going to compute this del 1, we need to consider both the backpropagated pathways or both the backpropagated weights associated with the pathways. That is, one is W14 and another is W15. In that case, only the direction of data flow is changed. You can see that signals are propagated from output to inputs one after the other. So this technique is used for all network layers, and you can see that if propagated errors came from few neurons, then they are also added. So in this manner, we can have all our error signal for each particular neuron. We can have this del 1, we can have this del 2, we can have this del 3, and This error, you know, now is going to take place a very vital role itself whenever we are going to now update the weights. So when the error signal of each neuron is computed, automatically weights are going to be modified. And as we know that now the updated weights or the modified weights will be the current weight plus eta del 1 d f1e by dex1, which is this is the kind of derivative of neuron activation function whose weights are modified. Now, in this manner, these weights are also computed. Similarly, all the weights are going to be computed. So, in this fashion, we can say that this particular training algorithm, this backpropagation algorithm, usually searches for weight values, right? That minimize the total error of the network over the set of training examples, that is the training set. And this backpropagation usually, consists of the repeated application, because here we can see that one is the process which is the forwarding process, right? Which is the forward pass, we can say. And also we can see one backwarding process or backpropagation process, which we can say as backward pass. So it is the combination of these two process, and it is the repeated application of these two processes as well. So we can say that in case of forward pass, the network is activated on one example, and obviously the error of each neuron of the output layer is computed whenever we are coming to the backward pass. So here basically we are going to update the weights due to the propagation of error in backward direction, starting from the output layer, and automatically that is coming to the input layer through the network layer by layer. So this is done by recursively computing the local gradient of each neuron, and that is why it is popularly mentioned that it uses gradient descent learning algorithm. Now, this is one, backpropagation learning algorithm. The pseudocode of this particular algorithm is given. If you ever want to or wish to work with this backpropagation linear algorithm, then this pseudocode will help you, or this training algorithm in pseudocode will help you to write a program. Now coming to the next neural network, which is called self-organizing feature map. Now, why it is necessary? This is a kind of, different sound neural network. So this is one feature map, and this feature map is self-organized. So what happens sometimes, we can have a wide pattern space, which is a very wide pattern, and we need to convert this wide pattern space into a typical feature space, like with a very reduced dimensionality, which is a kind of arbitrary dimensions to one dimensions or as two dimensions. Then it can preserve its neighbor topology, as well as it can convert this wide pattern space into a particular feature space. So what is this? What does this mean by neighbor topology? Neighbor topology means it can use, various kinds of topologies, where two topologies are mostly, used in case of self-organizing feature map, which is rectangular grid topology and hexagonal grid topology. Coming to the rectangular grid topology, you can see that in the outer box, you can see 24 nodes. In this particular box, in this particular rectangle or rectangular grid, you can say it here, only 60 nodes are there. Obviously, there are 8 nodes in the distance 0 grid. And this is something the winning unit, which is indicated by hash. So what does this mean by distance 0 grid? That means here the distance is the smallest. That means we can say there is a distance is 0. Here the distance is 1. We have one, a particular grid in between these two. This is the distance 2 grid because we have two different grids if we want to reach from here to here. So in every manner, you can see that the difference between each rectangular grid is 8 nodes. And obviously the winning unit is this one. So this is what we call as rectangular grid topology. Now, if you can see the hexagonal grid topology, then some self-organizing feature map works in this manner that here you can see this is the winning unit. So this is the distance 0 grid where we have 6 nodes in the hexagonal shape. In the distance 1 grid, we have 12 nodes. In the distance 2 grid, we have 18 nodes. So in that fashion, we can say that the difference between each rectangular grid is 6 nodes. Now, how does this architecture work? This architecture works in a very, similar fashion what we have learned in case of competitive network. So in that particular network, with the help of this neighborhood topologies, the training can take place over the extended region of the network. So it is exactly the similar process how the competitive learning takes place. So in that very case, we can, at the very beginning, initialize the weights. Obviously, along with that weights, we have to initialize the learning rate as well, and also the neighborhood topological scheme, that which scheme we are going to follow, whether it is hexagonal, whether it is rectangular, which one. Now, obviously, whenever we are going to initialize any kind of training, there must be a stopping criteria. So until and unless we have reached the stopping criteria, till then, we need to perform certain steps. And we need to repeat those steps, right? We need to repeat those steps for every input vector x. So what we need to do is, first of all, we need to calculate some distance matrix. That distance matrix, we name it as square of Euclidean distance. So this Euclidean distance, we need to measure with a kind of, whatever be the input vector it is, and where is basically we need to reach. So what is the distance between both these neurons or both these vectors? Whatever be the distance, we are going to find out the minimum Euclidean distance, right? Minimum distance. That means, obviously, our winning unit lies where this particular Euclidean distance is minimum. When it is happened, then we need to calculate the new weight of the winning unit. So what is the particular computation formula? That is, now the new updated weight has been calculated or has been evaluated by taking the old weight, and also, you know, this difference between the old weight from the input for this particular neuron multiplied by the learning rate. So here, what happens that whenever we have obtained a new updated weight, we have also have the urge to update the learning rate as well. And that learning rate, is going to be updated like alpha t plus 1. That means the next updated learning rate is zero point 0.5 alpha t plus 1, that is zero point 0.5 alpha t. And what happens that in that particular case, we need to reduce the radius of topological scheme. That means at the beginning we were here, then again we need to, reduce the topological scheme radius, and by following this we need to, minimize the Euclidean distance, and at a particular point we have reached to the winning unit where the Euclidean distance will be minimum. So in this manner, every time when we repeat all those steps, we need to check for the stopping condition for the network. Now, coming to the two different types of neural network with whom we have started our very basic class of artificial neural network, that is supervised neural network and unsupervised neural network. Now, after completing all the various kind of neural networks, now we can easily, distinguish, or we can name it as example of supervised or unsupervised neural network. Now, we can see that after covering all those neural networks, and some of them are still, beyond the syllabus kind of things. So in this particular thing, we can see that perceptron, Madaline, backpropagation, delta learning rule, those are, supervised learning algorithm. Those neural network follow supervised learning algorithm, and that is why those are supervised neural network. Now there are some support vector machines and k-nearest neighbor. Those are not, covered here because the scope is very limited. And still, all these neural network which are covered here, that is also, some of them also, are not in the syllabus directly, but you don't know, you can expect any kind of questions in the semester exam. Sometimes it may happen. So, on the contrary, unsupervised neural network has certain examples like the last one, which is the coherent self-organizing feature map. Obviously, some competitive learning rules as well. And there are two different, neural network which comes under this unsupervised neural network, which are the two very popular unsupervised neural network. One is k-means clustering, another is principal component analysis. So it may happen that in anywhere, you are asked to name some example of supervised and unsupervised neural network, because these are the, two broad categories of neural network. And moving to that, this is some deep learning, which is very popular these days. You can hear about this particular term, where I would like to mention that this deep learning, the very popular one, the very trendy one for today's market. So this deep learning can be used as supervised neural network as well as unsupervised neural network, right? because whenever it is used as a supervised neural network, it can be used as used for image classification. It can be used for object recognition or face recognition. Whereas whenever it is used as unsupervised neural network, it can be used as word embedding. It can be used for image encoding as well. So this can be used as supervised or unsupervised neural network. Apart from this deep learning, there is another neural network which can be named as a decision tree neural network, and this decision tree can be used as supervised and unsupervised neural network in both the cases, right? So now, after completing all these topics, now we have come to a point where we can discuss some application scope of artificial neural network. So, whenever we have these ample variations of artificial neural network, then automatically we can expect, a number of different application scope as well. So starting with air traffic control could be, automated with the location, altitude, direction, and speed of each radar, which is taken as input to the network. And in that particular case, the output would be the air traffic controller's instruction in response to each this radar signal. Second one can be appraisal and valuation of any object like property, buildings, automobiles, machinery, etc. And this can be an easy task for a neural network. Criminal sentencing, that could be predicted using a large sample of crime details, you can say as input, and the resulting sentences as output. Then there is modeling of complex physical and chemical processes, like it may involve, the interaction of numerous mathematical formulas that can be modeled heuristically using a neural network, and data mining, cleaning, and validation that could be achieved by determining which records suspiciously, diverge from the patterns of their peers. Sometimes it may happen that you can have a kind of, target prediction process from echo patterns. So what happens then that then the echo patterns from sonar or radar or seismic or instrument or magnetic instruments could be used to predict their targets from some echo pattern. Employee hiring can be possible, can be even optimized, you can see, if the neural networks were able to predict which job applicant would show the best job performance. Now, next is fraud detection or fault detection, anything like whenever we can experience this kind of fault or fraud using credit cards, using insurance or taxes, and those particular faults can be automated using a neural network analysis of past incidents. Recognition of handwriting and typewriting, that could be imposed by using a grid over the writing, where each square of the grid becomes an input to the neural network, and this may be called as optical character recognition, Then water level prediction, automatically, obviously, lake water levels or river water levels could be predicted based upon, precipitation patterns, and obviously the river flows or dam flows based on these. Then automation of machinery control. That means machinery control also can be automated, by capturing the actions of experienced machine operators into a neural network. Then medical diagnosis, which is an ideal application, I can say, for neural network, because and this is nowadays in a trend also, you know. So all these are application from this slide. And from the second slide, music composition can be tried using a neural network, because in that case, the neural network can be trained to recognize patterns in the pitch and tempo of certain music, and then the network can write its own music also. Then photos and fingerprint recognition can be done. That can be recognized by imposing a fine grid over the photo, and each square of the grid then becomes an input to the neural network, as I just mentioned earlier, for an example. Now, optimization of recipes and chemical formulations, that is also can be possible based on the predicted outcome of a formula change. And then scheduling of buses, airplanes, and elevators could be optimized by predicting demand. Staff scheduling requirements for restaurants, retail stores, or banks, or police stations, etc. That could be predicted, based on the customer flow, or you can say day of week, pay days, or holidays, weather, season, etc. Then designing strategies of games and business in this particular, on this particular point, it is very interesting, since uh, most of you are very much interested in mobile games. So strategies of this particular games or business can be also, captured by analyzing the expert player's response to given stimuli. Now, for example, a football coach must decide whether to kick or whether to pass or run on the last down, right? So the inputs for this decision include score, time, field location, or you can say yards to finish down, etc. There can be prediction of traffic flows, because in that particular method, signal timing could be optimized. That is a very useful, application. The neural network could recognize a weekday morning rush hour also during a school holiday, or a typical winter, Sunday morning, or chilly evening, anything. So this is all about prediction of traffic flows. Coming to voice recognition, because this could be obtained, by analyzing the audio oscilloscope pattern, much like a stock market graph, basically. So this can be happen also. And weather prediction may be possible also, because inputs here include the weather reports from surrounding areas, whereas outputs can be the future weather in specific areas based on the input information. So effects such as ocean currents and jet streams could be included here to, to obtain a better weather prediction reports, with much more, useful information. And many more applications can be there, can be possible with the help of artificial neural network. Now, when we have completed the artificial neural network, we have already gathered some knowledge about some fuzzy logic. We have already, have a strong now background on genetic algorithm. So why don't we, discuss about our last segment of the syllabus, which is the hybrid system. So whenever we are talking about, hybrid systems, so these systems can be classified into three different systems, One is neurofuzzy hybrid systems, another is neurogenetic algorithm hybrid systems, or you can say neurogenetic hybrid systems, whatever it may be. And also the third one is fuzzy GA hybrid systems or fuzzy genetic hybrid systems. So we are going to discuss one by one in a very brief manner. That is starting with neurofuzzy hybrid systems. This particular systems, that uses a learning algorithm. That learning algorithm is derived from or inspired by a neural network theory. And this particular thing is basically, aiming to determine its parameter, the parameter of a fuzzy system. So what could be the parameter of a fuzzy system? Those are fuzzy sets. We know that those are fuzzy rules. So altogether, what happens that this particular, fuzzy system is going to process the data samples so that it can use a learning algorithm, which is based on neural network, to determine its parameter, which is the fuzzy sets and fuzzy rules. So here what happens that this fuzzy hybrid system now becomes a combination of fuzzy set theory, as you can see, and neural networks having advantages of both. So these fuzzy systems, deal with explicit knowledge that can be understood, well understood in fact. And fuzzy logic, provides more reliable output when, this extrapolation is needed beyond the training data. So that means whenever we are going to deal with this kind of hybrid systems, it can combine the advantages of these fuzzy systems like this, and also, the neural networks which deal with implicit knowledge that can be acquired by learning. So neural network learning provides a good way, to adjust the knowledge of the expert. Expert means the artificial intelligence systems, you can say, and automatically, generate this additional fuzzy rules and, membership functions so that it can meet certain specifications. So in this manner, it helps reduce design time and cost. And on the other hand, fuzzy logic enhances, the generalization capability of a neural network system by providing more reliable output when, this kind of extrapolation is needed. So this is all about neurofuzzy hybrid systems. Now coming to the neuro-GA hybrid systems, then we can see that genetic algorithms have been, increasingly applied in artificial neural network design in several ways, like topology optimization, like genetic training algorithms, like control parameter optimization, and so and so. So in topology optimization, GA is used to select a topology, basically a number of hidden layers. So automatically number of hidden nodes, somewhere interconnection patterns. So in that way, for a particular artificial neural network, which in turn, is trained using some training scheme. Most commonly, backpropagation algorithm is well suited for the topology optimization. And in case of genetic training algorithm, we can see that the learning of an artificial neural network, is formulated as a weight optimization problem, usually using the inverse mean squared error as a fitness function or fitness measure, you can say. So many of the control parameters such as, learning rate, momentum rate, or tolerance level, etc., can also be, optimized using these genetic algorithms. In addition, we can, mention that genetic algorithms have been used in many other innovative ways also, so that we can create new indicators based on the existing ones, or we can select good indicators, or we can evolve optimal training systems, and complement other techniques such as fuzzy logic. Now coming to the third hybrid systems, which is the last one, which is called fuzzy GA hybrid systems. Now the optimization abilities of genetic algorithms are used to develop the best set of rules to be used by a fuzzy inference engine and to optimize the choice of membership functions. So what happens that a particular use of genetic algorithms in fuzzy classification systems where an object is classified on the basis of linguistic variables or linguistic values of the object attributes. Now the most difficult part of building a system like this is to find the appropriate set of fuzzy rules. The most obvious approach is what that can be to obtain a knowledge from experts and translate this into a set of fuzzy rules. But this particular, method is very time consuming. Also, sometimes it may be found that experts may not be able, to put their knowledge into an appropriate form of words. So in that very case, a second approach can be taken. So what was that? This approach is to obtain the fuzzy rules through machine learning, whereby the knowledge is automatically extracted or deduced from sample cases. So in that very case, you can see that a fuzzy genetic algorithm is a directed random search over all discrete or fuzzy subsets of an interval and has features, which make it applicable for solving this problem. It is capable of creating the classification rules for a fuzzy system where objects, are classified by linguistic terms and coding the rules genetically, enables the system so that it can deal with multi-valued fuzzy logic, and it is more efficient, as it consistent with some numeric coding of fuzzy examples. Now, what happens that the training data and randomly generated rules are combined so that it can create the initial population, giving a better starting point for reproduction. And finally, a fitness function measures the strength of the rules and also the balancing the quality and diversity of the population. So in that manner, this fuzzy GA hybrid systems work, and also we can understand that all these three types of hybrid systems work in this fashion. Now I would like to end today's class, and I hope you understood all through the lectures. If you have any query, then you can ask me personally. Now